Flow Batteries by Akash, Ashton, Emily, Mitchell, and Tom. Zinc bromide batteries convert the chemical potential spontaneous reaction of zinc metal and bromine into the electrical potential to supply current. How do they work? Zinc bromide flow batteries are rechargeable and use liquid electrodes to store and release chemical energy. The battery consists of two electrode tanks that contain a zinc bromide electrolyte solution, which is separated by an ion exchange membrane. The battery also includes two pumps to allow electrolyte movement from the reservoirs and negative and positive electrodes. During charging, the electrolyte solution from one tank is pumped through the ion membrane into the other. Zinc ions migrate to the negative electrode where they accept electrons and are reduced to zinc metal. Bromide ions migrate to the positive electrode, where they donate electrons and become bromine. During charging, the electrolyte solution from one tank is pumped through the ion membrane into the other. Zinc ions migrate to the negative electrode, where they accept electrons and are reduced to zinc metal. Bromide ions migrate to the positive electrode, where they donate electrons and become bromine gas dissolved in the electrolyte solution. These processes are managed by the electrolyte solution, which controls the movement of ions and the location of bromine, which keeps the battery charged for longer periods. How do they work? During discharge, the chemical energy is converted to electrical as the process is reversed, with bromine relocating to the negative electrode and zinc ions migrating to the positive electrode. The ion exchange membrane impedes the diffusion of bromine to the zinc deposit, which reduces the direct chemical reaction. Within the battery's electrolyte, there is an internal flow of positive ions that occurs in the same direction as the external flow of electrons, which keeps the overall charges balanced. The powerful pumps that are used to transport the electrolyte solution with sufficient velocity add a parasitic load on the battery. This inhibits the batteries from starting after run flat without an external power source used initially. The parasitic load takes energy from the battery to enhance the battery's ability to create more. In this case, when there is no charge, it is unable to do so. However, unlike normal batteries, zinc bromide batteries can be discharged down to zero without causing damage and can continue charging and discharging efficiently for thousands of cycles with negligible loss of capacity. Energy density and round-trip efficiency. The energy density of this battery sits at an average of 30 to 50 watt-hours per kilogram, with a round-trip efficiency of 70 to 80%. This means that for every unit of energy stored within the battery, only 0.7 to 0.8 units can be retrieved. However, this is also dependent on several factors, such as the size of the battery, its operating conditions, and the specific application. The round-trip efficiency can be improved by optimizing the battery's operating conditions, which may include the flow rate of the electrolyte solution, the battery temperature, and the charging or discharging rates. In comparison to similar battery types such as the non-flow zinc bromide battery created by University of Sydney's Professor Thomas Maschmeyer, the flow model does respectively have a substantial efficiency loss. Maschmeyer's non-flow model has a round-trip efficiency of 87% and an energy density of 120 watt-hours per kilogram. Maschmeyer's company, Gelion, have improved the efficiency of the battery by removing the electrolyte solution and opting for a patented gel. This evolution of the zinc bromine flow battery delivers performance with a simpler and more compact design to limit energy loss and remove the need for parasitic pumps. How much energy can be stored? How much energy can be stored is solely dependent on the size of the battery and its weight. On average, these batteries can store 30 to 50 watt-hours of energy per kilogram of battery. This, however, is significantly lower than the 200 watt-hours of energy per kilogram achieved with lithium-ion batteries. However, Primus Power, an American-based energy company, has produced a large 125 kilowatt hour zinc bromide flow battery. Possible applications. Possible applications for this battery type may include grid-scale energy storage or providing remote areas with power systems. They are well suited for large-scale energy storage applications, such as storing excess energy created by wind or solar farms, and or providing backup power to critical infrastructure, such as hospitals and schools. By storing excess energy, they can provide stability during peak energy consumption times or during energy strains in weather phenomena. The discharge time of 4 to 8 hours provides a solution for shifting renewable energy from when it's generated to when it's needed. This will aid in moving renewable energy sources to the forefront of energy production. These batteries can be used to provide power to remote locations where grid power is unavailable and or unreliable. As of 2021, Gelion has started work to provide remote areas of Papua New Guinea with 100 megawatt hour zinc bromide batteries to bring energy independence to the region. This subsequently provides the local area with new streams of income and job opportunities. Lifetime and cost. The lifetime of these batteries is particularly dependent on correct maintenance and upkeep. These batteries average a lifespan of 10 to 20 years when maintained, which averages over 11,000 cycles. The cost of these batteries is dependent on the model and make, but they average $300 to $5,000 per kilowatt hour storage capacity. Newer models and concepts have a lower price, such as Gelion, which has a model that costs $100 per kilowatt hour storage capacity. These batteries are exceptionally well designed and protected from the elements as their housing is robust. The internal components can be serviced and replaced individually, which both aids in sustainability and the overall lifetime of the battery. Safety. These batteries are a safe alternative to lithium-ion batteries as they do not contain any harmful materials. The battery contains no reactive or flammable materials. It has an inbuilt flame retardant within the electrolyte solution. There are no toxic metals contained within the battery or any of its components. Overall, the battery is safe to handle and there is little risk associated with it. The battery can also work effectively at temperatures as high as 50 degrees Celsius without a cooling system or needing to be turned off, which is a benefit when it comes to remote Australia and its weather conditions. Environmental impacts. These batteries are considered some of the most environmentally friendly designs as they are able to be produced and recycled in pre-existing lead-acid battery facilities with similar costs in their construction and disposal. There are only 4 unique steps that must be taken to produce these batteries, and the same casings can be used as those in lead-acid batteries. As the batteries do not contain any toxic metals or strong acids, the risk of environmental harm from incorrect disposal is minimal and does not pose a large threat. The materials used within the battery, zinc and bromide, are abundant materials, unlike lithium, and there are no ethical concerns when it comes to sourcing the materials. The battery itself has a rather low manufacturing carbon footprint, as it does not require high energy input or high temperature processing, unlike most batteries. As each component of the battery can be serviced individually, there is low impact on the environment with respect to new parts and new production. Each part of the battery can be recycled. This is including the electrolyte liquid or gel, which can be purified and reused in new or other batteries. Overall, the zinc bromide flow battery is sustainable and efficient. New models are proven to be effective and have aided in energy independence. The application of this battery will benefit not only the environment, but those with energy insecurity.